Here we're going to investigate rates of change. So hopefully you've already watched my video on tangent, secant, and difference quotient, which should enable you to fill out this first page. Rise, and the rise is 4 or negative 4, so let me just write that. The slope of the secant we can also write as rise over run, so negative 4 over the run of 1, which also gives us a slope of negative 4. Okay? Alright, now let's look at, let's look at the slope of the tangent at x equals 2. So recall what a tangent is. So recall what the tangent is. The tangent is the line. Let me just select the line tool here. The tangent is the, oops, not like that, is the line that just touches the graph at that point. So we see the point here that we're concerned with is x is 2. And we're going to draw the line that just touches that point. So it's going to look, it's easier if you have a ruler and you can sort of do trial and error with your ruler. But see how that just touches the line? This wouldn't work. This wouldn't work. This just touches the line at that point. There we go. And if we want to find the slope of the tangent, we can just use rise over run here, grade 9 styles. So we have the rise here of approximately 2 and the run of approximately 1. So the slope of this tangent, so I'm just going to write that, slope of the tangent is going to be approximately 2 over 1, which gives us a slope of approximately 2. Okay? So now, that's sort of an approximation of the slope of the tangent. Can we use the difference quotient to find a more accurate approximation of the slope of the tangent? Let's do that now. So the slope of the tangent is equal to, according to the difference quotient, it's going to be f at x plus h minus f at x all over h. So let's plug in our equation into that. So again, our equation is 2x squared. So instead of the x, I'm going to write 2x plus h squared. So you replace all the x's with x plus h's, minus 6x plus h plus 8. And this whole thing minus the f at x, right? Which is just going to be our original equation. I'm going to minus it, put that in brackets because we're going to have to distribute that brackets, that negative to all the terms. 6x plus 8. And don't forget that this is all over h. Okay, so before we continue simplifying this, an easier thing to do, since we know we're looking for x equals 2 for the tangent at x equals 2, let's just plug in that to 2 right now for x. So 2 plus h squared minus 6, 2 plus h plus 8 minus 2x squared, so that's going to be 4 times 2, which is 8, minus 12 plus 8, all over h. All right, now let's continue. So the first brackets here is going to be simplified as 4 plus 2h, which is 4h plus h squared, minus 12 minus 6h plus 8 minus, now I'm not going to cancel anything out yet or simplify anything over here, just because I want to show you what's going to happen. So these signs change here when we distribute that negative, all over h. You could simplify if you want, but I just want to show you what's going to happen, sort of cool. 8 plus 8h plus 2h squared minus 12 minus 6h plus 8 minus 8 plus 12 minus 8 all over h. Okay, that's a big ugly thing. But look, what can you find in there? You notice there's a lot of repeating terms. And this will always happen because you basically have two of the same equation, right, that you're plugging in a value for. So a lot of stuff is going to cancel out. So let's start canceling out. For example, I can see this plus 8 and this minus 8 are going to 0. This 8 at the beginning and this 8 at the end are going to 0. This positive 12 and this negative 12 are going to 0. And we are left with, just write out what we're left with, well, this 8h up here minus 6h, so we're going to have 2h plus 2h squared all over h. Whew, that's much nicer. We can simplify this further. I'm going to factor out an h in the top. Actually, I'm just going to factor out a 2h in the top because that's a common factor. 1 plus h all over h. And you should notice now that this h down here and this h up here are going to cancel each other out. Now, what do we do? Well, we can simplify this even more as 2 plus 2h, and that basically represents the slope of the tangent, right? So m of the tangent. So we're looking at this when h is very, very, very small, right? And the closer we get to 0 with h, the more accurate our answer is going to be. So I'm just going to plug in to this equation. H is a really small number. 2 plus 2 times, I don't know, 1 point, nope, not 1 point, 0.0001. Why not, right? So let me do that on my calculator. 2 plus 2 times 0.0001. That gives me a slope of the tangent as, I'm just going to write it down here, 2.0002. You'll notice that's very, very close to 2, which was our original answer. Now, the thing about it here, can't we just plug in h as 0? Wouldn't that solve our problem? Because if we plug in h as 0, notice what's going to happen here. This is going to go away, or this term's going to go away, and our slope is just going to be 2. And if we plug in numbers that are very, very close to 0, so if I plug in 0.000000001, it's just going to be even closer to 2. The problem with this, if you remember from the previous video, is that up here, right, if we look up here, what we did is we canceled out an h in the denominator. And whenever we do that, whenever we have a value in the denominator, we have to set a restriction, right? H cannot equal 0. If h is equal to 0, this thing's going to explode, right? You're going to be dividing by 0, which you can't do. So for now, up until this point, we've just been able to plug in very, very small numbers for h so that this doesn't happen. Well, there's another way. There's a bit of a cheating way, and that's called using the limit. So instead of using this definition for the slope of the tangent here, right, 2 plus 2h, what we can say is that the slope of the tangent is equal to the limit as h approaches 0 of 2 plus 2h. So essentially what we're going to do is we're going to trick the math a little bit, and we say, well, h is going to be very, 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 very close to 0. It's not going to be 0. It's going to be very, very, very close to 0, but so close that essentially we can make it 0. So we evaluate this as the limit of h, the limit as h approaches 0 is equal to 2 plus 2 times 0, okay, which just equals 2. So most accurately, the slope of the tangent at x equals 2 is equal to 2. This might seem like a bit of a technicality that we're allowed to plug in 0, but we're going to do a lesson on limits in the next unit, and you'll understand more about why. So just to look down here at our new definition for the slope of the tangent is the limit as h approaches 0 of the difference quotient, okay, f at x plus h minus f at x over h. So the thing about this, we're essentially going to use this limit to plug in h as 0, but we can't do that until we've removed this h from the denominator. So the goal of these kinds of questions is to first cancel out h, like we did here, in order to allow us to plug in h as 0. And you'll see that in the next example. Example 2 has us find another difference quotient of y equals 8 over 3 plus x. So let's first start off by writing our new definition of the instantaneous rate of change. I'm going to call, because it's actually asking for the instantaneous rate of change instead of the slope of the tangent. It's the same thing, but I'm going to call it IRC. So our new definition for this is the limit as h approaches 0 of our difference quotient. So f at x plus h minus f at x all over h. So again, we're just going to start off by plugging in that equation. Every time you write a new line, you have to include this limit part to be technically correct. So f at x plus h, so that's going to look like this. It's going to be 8 over 3. Instead of the x, we're going to put x plus h, so plus x plus h minus, minus 8 over 3 plus x, and this is all over h. We have fraction inception here. We have lots of fractions that we're going to have to deal with. So let's continue simplifying this. So the limit as h approaches 0. Notice how we can't plug in h yet because there is an 8 down here, h down here in the denominator. So if we tried it now, we wouldn't be able to do it. It would be undefined. The question is asking us for the slope of the tangent, or the IRC, at 1. So let's start off by plugging in 1 to simplify our calculations. So 3 plus 1 plus h, which is going to be 4 plus h, minus 8 over 3 plus 1, so 4, all over h. Okay, now we just have to do some fraction manipulation here. So lim h approaches 0. And what we can do is we can find a common denominator between these two terms, right? And the common denominator is going to be 4 times 4 plus h, right? Because there's no other common denominator there, so I'm going to write that part first. 4 plus h, that's our denominator. And in order to use that denominator, the 8 needs to be multiplied by 4. And the 8 over here needs to be multiplied by 4 plus h. Okay, so this is just finding a common denominator. This is all over h. Continuing on, the limit as h approaches 0, and 8 times 4, obviously, so we can simplify what's in the top, right? We're going to have 8 times 4 minus 8 times 4, which is just going to be 0, right? Minus 8 times h. So on the top, we're just going to end up with negative 8h all over 16 plus 4h all over h. All right, that works. Now, ugly fractionception here. So what we can do, remember, we can represent this h in the bottom as h over 1, right? So we're dividing this fraction on top, negative 8h over 16 plus 4h, divided by h over 1. And when we divide two fractions like that, we're going to multiply by the reciprocal, right? So the limit as h approaches 0 of negative 8h over 16 plus 4h times the reciprocal of h over 1, which is 1 over h. Notice what happens here. We have an h in the numerator here, an h in the denominator here. Those are going to cancel out. Nice. When those cancel out, notice how now in our equation, oops, let me continue writing in black there. When we plug this into our equation, are we allowed to plug in h as 0 now? We have an expression, so negative 8 times 1 is just negative 8, all over 16 plus 4h. That's what we're left with. If we plug in h as 0 now, is it going to be undefined? And the answer is no, it's not. So as soon as we've canceled out that h, removed it from the denominator so that it's not going to be undefined, we can plug in that limit h equals 0. So this is going to be negative 8 over 16 basically, because that we've plugged in h as 0 here. Simplifying this, this is just negative 1/2. So our instantaneous rate of change of our equation at x equals 1 is just going to be negative 1/2. Notice how the answer is also written up here. Okay? So let's look at example 3 now. It has us finding the difference quotient at x equals 4, or the instantaneous rate of change of root x plus 5. So again, I'm going to start off by writing out my difference quotient. IRC is equal to the limit as h approaches 0 of, what is it, f at x plus h minus f at x all over h, right? So again, I'm going to plug in this equation here. The limit as h approaches 0 of f at x plus h is just going to be the square root of x plus h, right? So I'm going to replace that x with x plus h plus 5 minus the square root of x plus 5 all over h. So obviously we can't plug in h yet because it would be undefined. We got to find a way to cancel out one of those h's, or that h in the denominator. So again, let's start off by plugging in x equals 4 because we know that's where we're looking for. It's going to simplify our math. So x plus h plus 5 is going to be 4 plus h plus 5, or 9 plus h, right, minus the square root of 4 plus 5. Well, I'm just going to write that as 4 plus 5 is 9, so the square root of 4 plus 5 is just going to be 3, all over h. Already looks a lot simpler. Now, there's a problem here. We can't cancel out these h's, right? One is under a square root. So think about a previous lesson. How did we get things out of that square root? How did we simplify things that had a square root? And the key is the conjugate. So we're not going to rationalize the denominator here. We're going to rationalize the numerator in order to free that h from under the root sign. So what that's going to look like, I'm going to multiply by the conjugate of root 9 plus h minus 3. So that's going to look like this. The conjugate of that, instead of 9 plus h minus 3, it's going to be plus 3. All over, and then I have to do the same thing in the denominator, right? 9 plus h plus 3. So I'm multiplying by the conjugate in the numerator and the denominator. So I'm going to let you do the algebra here. So pause the video, do the algebra, and then you can check your answer with me at the end. Okay, after all that algebra, your answer should come out to the instantaneous rate of change is 1 over 6, which agrees with the answer that I put on the page there. Let's go on to the next one. So this is the last example. I'm going to let you try it yourself, but just some background here. The trajectory of a rocket is given by this equation. So that's basically the distance above the ground that the rocket is at a given time. We've talked about this in class where the instantaneous rate of change of this equation is going to be the speed or velocity of that rocket. So essentially what we need to do is we need to find the instantaneous rate of change of this equation where t equals 4. Okay, so use what you know here. You can pause the video here and try it yourself, and then unpause to see the final solution. All right, here's the full solution. So the velocity comes out in the end to negative 10 meters per second, which in this case just means, the negative just means it's going downwards. Okay, there you go.